Our final presenter is Tian, representing the PhD program in Applied Mathematics.
So we live in a society which is becoming more and more reliant on computer modeling to predict future events. These computer models are often complex and difficult to understand, but essentially they all work the same way. You give the computer some model inputs and then you get a set of model predictions. For instance, a computational model to predict the spread of wildfires might take in things like temperature and wind speed and give you predictions of where and when a wildfire might go next. As these models become more influential in our policies and decision-making, it becomes increasingly important to know how confident we are in our predictions and measurements. If our model predicts that a wildfire is traveling at 15 miles per hour, are we certain? How certain are we? Could it actually be 5 miles per hour? Maybe it's not moving at all. What if our predictions aren't consistent compared to what we actually observe? There's a growing field of mathematics surrounding these questions called uncertainty quantification. In general, we seek to measure and quantify different types of uncertainty so that we can incorporate into our analysis and our understandings of our predictions. For example, maybe our predictions do not match our observations, but because we do not have accurate measures of our model inputs. So because we don't have accurate measures of our model inputs, then these two things are different. So one strategy to improve our model predictions is to incorporate our current observations to get better measurements of our model inputs. So what you would do is you take your observations, you try and update maybe what your guess was for your model inputs, and then maybe you'll get better model predictions. My thesis work involves a new method to incorporate observations to update your initial model inputs called data consistent inversion. One of the benefits of this method is that your predictions are more consistent with your observations, even when your initial measurements of your model inputs are not very precise. So my contribution to this method is to examine what happens when, in addition to your model inputs maybe not being super accurate, you also have potentially some inaccuracies in your actual computational model. Maybe you don't have all the modeled physics quite exactly right. Can you incorporate those measurements to improve your model inputs to get better predictions in that situation as well? Thanks.
All right. The judges will retire to Julie.